Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm AJ Brush. I'm delighted to introduce Kevin Lee, who's here to talk about his work in enabling eyes-free interaction by exploiting human experience. And usually I make people tell me a fun fact about themselves, but I didn't grill Kevin enough. But he is just recently back from Germany as of yesterday, so you can ask him tough time zone math questions if you should wish to at the end. So, Kevin.
Thanks, AJ. So at the core of today's talk is really this problem that people have difficulty interacting with their mobile devices when they can't actually look at them. And the main takeaway that I have for you today is that we can actually address this by using touch-based messages. And if we build them in such a way that take advantage of human experience, then they'll have some kind of pre-learned quality to them. So what I mean by that is if we base these touch-based messages on things that people are familiar with, like music, human touch, and speech, then whatever information mapping they have with those experiences will then carry over to these touch-based messages. And so in today's talk, I'm going to open up with a brief project I worked on here, actually, a couple years ago, on using auditory feedback to solve this eyes-free problem. And then for the remainder of the talk, I'm going to focus on touch-based communication. I'm going to first present a taxonomy that I've used to guide my exploration in this space of mapping things to touch. And then I'm going to talk about a series of projects that I've worked on looking at how you might map music, human touch, and speech to touch-based messaging. But before I dive in, I want to briefly talk about why we even need these new ways of interacting with devices when we can't look at them. And so to see why this is a problem, I want to start by looking at your typical desktop environment. So I'm sure you all have something like this at home or in your office. You have this nice big display for viewing information, and you have a keyboard and a mouse kind of dedicated for input. Unfortunately, kind of an inherent assumption in this setup is that the screen is always available to the user. And so as a result, this has been designed for the visual channel in mind. Unfortunately, this assumption no longer holds as people go mobile. If it did, then today's user would look very much like this, with a PC strapped on their back and a screen kind of glued in front of them. Instead, today's users look much more like this, right? Very highly mobile, always on the move, places to go, people to see. And lucky for us, we have these cell phones that we carry with us wherever, which have kind of become the de facto standard for mobile computing, right? And they're very cool, and you can see that the interfaces are still highly visual because they've kind of grown from traditional UI design. Unfortunately, there's a number of scenarios where this highly visual design won't work out so well. So using visual interfaces such as the iPhone when driving can be incredibly dangerous. In other situations, using visual channel can be highly disruptive to your situation. And then there are other times when using devices can be socially unacceptable. There's also a huge class of users who are visually impaired and can't even take advantage of visual interfaces, much less use them. And finally, we're seeing kind of as devices get smaller and smaller, we're seeing a new class of screenless devices. So these devices, such as the iPod Shuffle, don't even have displays. And so obviously, a visual interface would not work here. OK. So obviously, we need a way to support eyes-free interaction where people can't actually look at their devices. And so then the next question becomes, well, how do we actually enable this? So one possibility would be to use auditory feedback. And so I imagine many of you are familiar with this project, so I'm just going to very briefly go through it. So to ground this example in kind of a concrete usage scenario, I want to first show a typical scenario where a person might be trying to access phone content while talking on the phone.
Hi, Kevin. Can we meet sometime next week?
Oh, hi, John. Yeah, sounds great. Let me check my calendar. Hold on. When did you have in mind?
How about Tuesday morning sometime?
Let me check. Hold on.
after 11.
What did you say?
I was saying it has to be after 11, though.
Oh, yeah, no. I'm only free from 3 to 4.
Sorry, I have meetings all afternoon. How does Wednesday afternoon look?
Hold on, let me see.
And so you could see how looking at the device disrupted with the conversation. And so to address this problem, we built an application called blindSight. So blindSight is a Windows mobile application that runs on the phone and essentially launches when the phone call initiates. And so users can provide input by pressing these buttons on the phone and receive output in the form of auditory feedback. And so this allows a user to access information content on the phone when they can't necessarily look at it. You might be wondering why I'm holding the phone upside down here. So that's actually just one of the many form factors that we tried out when we were exploring that project. So you might think, well, with auditory feedback, this should be a fairly simple problem. You know, you could just read out information, whatever information prompts show up on the screen, you could just read that out to the user. And it turns out it's not that simple, because that would essentially give you what you get with interactive voice response menus. So you've all experienced this, where you call in to customer service, and then you get this long listing of details and different departments that you can contact, and you sort of have to wait for a really long time before you can actually press the option that you want. So we had to implement a number of different design options. And so in the interest of time, I'm only going to show one of the design options that we had to implement to actually make this work. And the video clip just describes it.
Hitting a button once describes that button's functionality. Calendar. Hitting the button again launches the function. Once users are familiar with the system, they can preempt announcements by double pressing in quick succession. Monday, 9 a.m.
And so that sort of gives you an idea of how users are able to launch applications that are kind of running on this phone. And again, I'm leaving out a lot of details here, but I just want to show you a brief demo video to give you an idea of what we ended up with. I want to point out that this is fast usage by an expert user, namely myself. And it might seem a little confusing to someone who's seeing it for the first time, but I should point out that we did give this to completely unexperienced users at the end with a user study, and they were able to pick this up within a couple minutes of use.
Using blindSight, the previous conversation might go like this.
Hi, Kevin. Can we meet sometime next week?
Oh, hi, John.
Monday,
yeah,
9
sounds great.
a.m. next
When did
Monday.
you have in mind?
How about Tuesday
Next
morning
Tuesday.
sometime?
Noon.
I'm busy in the morning, but I'm free in the early afternoon.
Sorry. I have meetings all afternoon. How does Wednesday afternoon look?
Wednesday.
Yeah, Wednesday sounds good.
31.
I am free after 1.
Okay. Let's make it 1 then. Call me on my mobile
Block,
phone
save.
if anything comes up.
Will do. Can
Oh.
you give me your number again?
Add, enter number.
Sure. Do you have something to write with?
Yep.
It's
5,
555
5, 5.
Uh-huh.
123
1, 2, 3,
7324.
7, 3, 2, 4.
Of
Save.
course.
Home.
Oh, and if anything comes up, call me
Find
the AI
enter
lab.
name. 3, 1.
Their number is
AI lab. 4, 2, 5.
2.
Oh, wait. Let me find something to write that down with.
So I think it's worth discussing a number of the different properties involved here with audio feedback. So on the plus side, it's easily learnable, right? You could see that anyone who understands English could more or less pick up the system, and that's kind of what we saw in our user study as well. And you can convey lots of information just by reading out information to the user. Unfortunately, it's not usable in all scenarios. So loud environments such as concerts, you probably wouldn't be able to use something like this because you wouldn't be able to hear the feedback. And obviously, having a phone talk to you in the middle of a meeting is probably still going to be socially disruptive. So we need something else. And so for this, touch is kind of an interesting alternative to auditory feedback, as it might address some of the shortcomings that I just discussed. So conveying binary information using touch is pretty easy. And I'm sure you all have experience with this, right? Your vibrating phone tells you when someone's actually calling. It doesn't really tell you much more than that, but you are able to receive this information. And so to convey more complex information, you could imagine using multiple vibrators. And this is essentially what Lorna Brown did with her multidimensional tactons project. So she mounted a couple different actuators on a user's arm, and by varying amplitude and duration, she created a whole bunch of different unique vibration patterns that users were able to identify and distinguish. And you could take this approach a step further and essentially generate vibration Morse code. And so psychologist Frank Gildard did this in the 50s, where he mounted 5 different actuators on a user's chest, and he varied intensity and duration for each one of these actuators and mapped a different signal to different letters of the alphabet. And he found that after 65 hours of training, users were able to start receiving messages at about 35 words per minute. So this is great because it shows that you can convey a lot of information using touch. But obviously, we would like something where you don't have to spend so much time learning these messages. And so the question now becomes, can we come up with something that's not so abstract, something that's a little easier to learn? And so as we started thinking about this space, we decided to kind of look at how people interact with the world eyes-free in the absence of technology, right? And so if you think about it, as people, we have 5 different senses available to us. Obviously, the sense of sight is out, but we still have our sense of hearing, which we use all the time, right? Smell, taste, and touch. And so if we think about how we might map these different senses to touch-based messages, obviously taste and smell are very interesting, but they don't have very straightforward computational equivalents. I know people are working in that space, but I'm going to leave them out of this discussion. And so for the remainder of today, I'm going to focus on how you might map things that you experience through touch and through hearing to touch-based messages. And so you could imagine first, if we talk only about the touch-based channel, you could imagine breaking up this space into really touching other objects and other people. And within each one of these categories, you can imagine a different project looking at the options in that space. And so in the case of people touching other objects, you could imagine exploring a project looking at how you might simulate the feeling of buttons on touchscreens, for example. A lot of phone manufacturers are actually working on that problem, and so I will not talk about that today. In the humans touching other humans category, I'll be talking about a project looking at how you might map human touch to a form of computer-mediated touch. And then moving over to the hearing category, you could again divide that space into non-speech auditory cues and speech auditory cues. And I'll be talking about a project looking at mapping music and sound effects to vibrations, as well as a project looking at a tactile encoding of speech. And so the first project I'll be talking about is looking at how we can map music to vibrations. And obviously, sound is really just another form of vibration. And so when I talk about vibrations here, I really mean mobile phone vibrations, which are kind of on the order of 250 hertz. And so you might be wondering, well, why are we even talking about this? Why do we need a vibrotactile encoding of music? And so the most common example I give for this is vibrotactile ringtone. So we currently have auditory ringtones where you hear the ringtone and you're able to tell exactly who is calling you. But we don't have a straightforward tactile equivalent. And you could imagine if we could map that music cue to a vibration, then users could tell who was calling based on this vibrotactile cue. And so the problem we're faced with here is that we want to convert music to these different vibrations. And so to do so, we're going to need vibrations of varying intensity. Unfortunately, the phone's vibrator, as exposed through the typical phone developer API, only turns on and off. And it does so only at a single frequency and a single amplitude. And so to generate these different levels, we're going to need something here. And so what we did was we applied something similar to pulse width modulation, which is commonly used with motors. So for those of you who aren't familiar, the general idea here is if you think about, actually modern day light dimmers use this. So if you enter a room and the light's off, it's too dark. And so you turn the light on, but then the room's too bright. And so what you can do is you can stand there and rapidly flip the switch on and off. And what you'll get, if you switch it fast enough, is you'll get kind of this medium level of light intensity in the room. And by varying how long you turn the light switch on for before you turn it off, you can kind of vary the intensity of light in the room. And so if you apply this same concept to motors, what you essentially get is you get the ability to change the rate at which your motor rotates. And when you do this with vibration motors, you essentially get different or varying levels of vibration intensity. And so we did this using commodity smartphone motors on a phone that has Windows Mobile running on it. And we found that we were able to produce 10 user differentiable intensities of about 20 milliseconds long. And so when we tried playing vibration pulses shorter than 20 milliseconds, it just didn't work very well. And I think it has to do with the fact that the motor doesn't spin up quickly enough in those situations. And so moving back to this problem of this higher level problem of trying to map music to vibrations, obviously there's a ton of information in the music information retrieval literature for how people identify different types of music. And it turns out beat and lyrics are kind of the two most important characteristics for identifying music. And that kind of makes sense if you think about how you yourself think about different types of songs. Unfortunately, yes?
I was wondering, 20 milliseconds is 50 hertz.
Yes.
50 hertz is a normal, roughly, spin frequency of a pager motor. So how could you get pulse widths at 20 milliseconds?
So
That means you can spin it once and turn it off.
So the pulse, the width of the pulse is actually much shorter than 20 milliseconds.
The PWM pulse or the actual vibration pulse you feel?
The PWM. So the full duty cycle is 20 milliseconds, but kind of if you just flick it on real quickly. Okay, so you've got beat and you've got lyrics. It turns out that when you try to map these to the 50 hertz equivalent, it really doesn't work out so well just because of the high disparity in fidelity. And so what we ended up using was to try to convey the current energy level of the music instead of these kind of macro level properties. And so shown over here is the high level process that we used, and I'll go into each step in more detail now. So the first step is to apply a common bandpass filter to the signal to remove noise. And when I say noise, I'm referring both to kind of noise in the very traditional sense of signal and noise ratio, but also a lot of these elements that I talked about earlier, such as lyrics and things like that. And then we use amplitude thresholding to further reduce some of the less important elements. And all this is done in the time domain. And then we take a running sum of absolute values, effectively performing rectification, and we take one value for every 20 milliseconds of signal. And that allows us to maintain signal duration to be consistent between the audio and the vibration equivalent. And then in the last step, we just exaggerate the features by composing the previous output with an exponential curve. And shown here is the generalized form for that. And we had to apply a number of different constants just because we had to tweak it a little bit for different songs. So to give you an idea of what this actually feels like, I have a phone demo with me, but obviously I can't put a phone in everyone's hands, but you're welcome to try it after the talk. So what I've done is I've recorded the sound of the vibrating phone on my laptop. And so this will require a little bit of imagination on your part. So first is the audio equivalent of Beethoven's Fifth, which I'm sure you're all familiar with. And then the vibro-tactile equivalent. It feels much better than it sounds. And another more contemporary song. And the corresponding vibro-tactile sequence. Okay, so now we have a way of mapping music and sound to different vibrations. And so then the next question becomes, will this work in the wild? And so to try this out, we built a buddy proximity notification system. And so this is an application that's running on Windows mobile phones. And it basically supports two different states of proximity, nearby and far away. And so when a buddy is close, it plays the corresponding song associated with that buddy. And if the phone is in vibrate mode, then we play the matching or corresponding vibro-tactile cue. And so obviously there's a number of system-level components involved here that I won't talk about today, but the details are in our Mobisys paper. And so just focusing on the user study, we gave this to 3 groups of friends who carried it around with them over the course of 2 weeks. And so these 17 participants were divided into 3 different usage groups. And so the main thing to focus on here is the different cue conditions. We had nature sounds, which is just commonly used nature sounds based on the peripheral cue literature. And we had your choice, where you would select what your friends would hear when you guys became close to each other. And then the my choice condition, you yourself would select what you would hear when your friends came close by. And to give you an idea of how users use this, here's a quote taken from a user at the end of the study. One time at the library, I wanted to eat with someone, and so I went outside to call someone. The phone vibrated. I just called the person to meet up. So you can see how this kind of supports this nice to know information without kind of requiring users to have to look at the phone. And so the main level takeaway from the study is really shown here, where we asked users whether they could identify who it was after the cues played. And so every time after a cue, a form popped up on the phone, and they would answer it either then or answer it later. And again, the high-level point is really just that the two music conditions performed better than the nature cue condition.
So did they have their phone vibrate on the study?
So that was one thing that wasn't very well controlled, because people, depending on their context, would often change the phone from the different conditions. And so unfortunately, we didn't actually record what percentage of the time people had their phone in vibrate versus audio.
And was there a vibrate equivalent of the nature
Yes.
cues?
Yes. It's the same algorithm as the music algorithm.
Afterwards, did you do like a post-test with them, where you just played like a quiz where you just played each of the vibrate?
Yeah, so we did a pre-study and a post-study. The details I won't talk about here. The thing we were interested in there was actually, I guess I could talk about briefly. The thing we were interested in there was that I personally expected to see some form of learning taking time, occurring over the course of the study. But it turns out that there were no significant learning effects. And so people were very good at identifying the cues just right off the bat for songs that they knew really well, both before and after the study. But for like the sound cues and for the songs that people weren't familiar with, they were equally bad in the beginning and at the end. For the vibration, yeah. So that was kind of an interesting finding. So based on some of these findings from our study, at a higher level, there's some interesting takeaways for designing peripheral cues in the wild. So the first finding is that we actually get these higher comprehension rates when users select their own cues, and that kind of alludes to what I mentioned a few minutes ago. And I also touched on this, that mapping music to vibration was more successful for people who actually knew the songs well. And the third point is that it turns out that semantic association is sort of key to learnability. And I don't mean learnability over time. I guess I kind of mean more of this pre-learned ability. So people were able to map these vibrations to songs with 75%. I mean, 75% of the participants were able to just get it for all of the songs that we mapped right off the bat. And so this might seem like an obvious finding to people outside of HCI. And I just wanted to point out that in the peripheral cue literature, it's often suggested to use nature cues because they're unobtrusive and they kind of blend in with the environment. And I guess I just wanted to point out that for certain types of applications, music actually might be more effective if it has this strong semantic association. Okay, so at a higher level, it turns out that vibration seems to work well for trying to map music to these tactile cues. But we do need more expressive touch for kind of other things. So as I pointed out, vibration was a very low fidelity signaling mechanism, and we need something more interesting for conveying more information. And so that leads me to the next project that I'll talk about, which is looking at computer-mediated human touch. And so the idea here is that there's certain things that we convey with human touch that make much more sense than communicating with vibration. And so if you look into the psychology literature, human touch is actually really good for conveying emotive aspects or intent. And you can imagine some kind of tapping and rubbing coming from your phone that would presumably tell you how urgent a phone call is, for example. And so, again, everyone here is familiar with a tap on the shoulder or a rub on the back when kind of your friend might be feeling down and out. But modern-day mobile phones don't support any of that, right? All they do is they vibrate. So shown here is a vibrotactile actuator pulled out of your typical phone that I'm sure it's in every single one of your phones in the audience. And I think it's worth talking about briefly here because it has two problems, really. So the way it works is it's got this offset weight connected to a rotational motor. And when you turn the motor on, this offset weight starts spinning around. And after it kind of reaches full speed, the entire body of the device starts vibrating. And the two problems that I see with this really are, first of all, that because it is kind of this rotational device, all you get out of it is vibration. And so you can turn it on and off quickly, as I mentioned earlier, or you can turn it on at different rates, but at the end of the day, all it does is vibrate. And the second problem, which I think is the bigger problem, is that people don't actually go around vibrating each other as a form of communication, right? And when they do, it's usually not a good thing. And so the observation here is that people instead tap and rub each other. And so if we as people do this, why can't we do this with our devices? And that's kind of the motivation behind the project that we looked at here, which was trying to recreate tapping and rubbing. And so I'll be talking about two prototypes that we built to explore this idea. And both of them are really based on this underlying technology of voice coil motors. So this technology is commonly found in hard disk drives. So you'll find one of these. This is taken out of a standard hard drive that you find in your computer. And I'll briefly talk about it. So the way this works is that you have these coils of wires sandwiched between two permanent magnets. And when you kind of change the voltage going through these coils, that allows you to move the head back and forth. And so what's nice about this, as opposed to the vibration actuator that I showed earlier, is first of all, the coils are really light, right? There's no offset weight, and the magnet isn't actually attached to the armature. And so the result is you get a nice low mechanical latency with kind of the startup of this device. And the second thing is that it kind of sweeps laterally instead of this rotational action that the vibration motor was giving us. And so this allows us to explore a couple of different alternatives to vibration. And the final point I want to point out is that you might think that this is really big and heavy, and there's no way that this could ever actually be on a mobile device. But it turns out that with customized forms of these actuators, these things could be much smaller, right? So shown here is IBM's microdrive technology, which they developed in the early 2000s, like 2001, 2002, as an alternative to solid-state memory for compact flash. And so this is really just a small hard drive that basically would sit in compact flash form factor. The idea is that you would be able to support higher memory densities than what solid-state could support at the time, which is great for us just because it shows that you could really have a smaller hard drive motor. And so shown here is kind of the setup for how we actually use this actuator to drive our different prototypes. So to generate a signal, we wanted to use the audio output on the computer. But this signal actually turned out to be too weak. And so we had to connect it to a custom audio amplifier, which allowed us to boost the signal along with some filters to filter out kind of low-level noise, which we then connected to a voice coil motor shown over there. And this allowed us to basically control the device by using the laptop. Shown here is our tapping prototype. We've attached a hammer to the voice coil motor, which allows us to generate tapping sensations by moving the contact head orthogonally to the contact surface. Shown here is the rubbing prototype, again using the voice coil motor, but moving the contact head laterally across the skin surface to generate a rubbing sensation. Here's another view of the rubbing prototype. You can see that the user would place their hand over this gray window, and the white head that you see is actually the contact head that we use for generating the rubbing. What it is it's Teflon tape coated over a hollow plastic shell, which kind of has this human flesh-like quality to it. And if you remove the window, you can see that the head is attached to this arm, again using the voice coil motor for actuation, to move it laterally across the skin surface. Okay, so now we've got a prototype. We wanted to see if this actually felt like tapping and rubbing, and so we ran some user studies. We recruited 16 participants in a within subjects design for the tapping study, and we generated taps using a 250 millisecond square wave. And I know Mike's going to call me out on this, so I'm just going to say up front that it wasn't a true square wave because of the bandpass properties of the sound card, but more of an approximated one. But it was, for the most part, good enough for our purposes. And so we exposed users to taps of different strength and speed, and we had a number of different speed conditions. So because we wanted to use different speeds, but we originally wanted to keep these tap sequences of constant duration. But what happened was, in some of our pilot studies, we found that, well, if you change speed but you leave duration constant, then you're going to end up with different sequences with different number of taps. And people said, well, I would just count the number of taps and that would tell me which sequence was faster. So we had to break the speed condition into these two subconditions of constant number of taps or constant duration, where you essentially vary the number of taps. We collected both quantitative and qualitative data. In the interest of time, I'm not going to talk about the quantitative aspects, but we'll instead be focusing on the qualitative aspects, because we were most interested in whether we could actually recreate this human experience. And so after the study, we asked users, if you had to explain if you had to describe these sensations to someone who wasn't familiar with this, what would you say? How would you describe it? And we asked them which aspects of the experience felt natural. And finally, we said, if your phone could generate this in kind of an open-ended session, what would you want to use these kind of sensations for? And so we were very careful throughout this process to not use the terms tap or rub or anything suggestive of human contact, because we wanted to see what they would say. And so it turns out that tapping actually mimics the real thing. So 13 of our 16 participants in the tapping study actually used the term tap when describing the sensation. And the people who didn't use terms like drumming their fingers on a table or kind of a tickling sensation or these very human-like qualities. It's also worth pointing out that the fast and slow taps are perceptually different. So people consistently said that the slow taps felt much more human, whereas the fast taps felt more mechanical, like a vibration. And that's also interesting, I think, because it further reinforces this idea that vibrations really just aren't a natural or human form of contact. Our rubbing situation setup was very much the same. The main difference was that we didn't have an amplitude condition, because if you think about it, swinging the rubbing actuator faster across the skin is really the same as moving it faster. So there's no need for an amplitude condition, and so we only had 8 participants. Again, I'm only going to focus on the qualitative aspects of the study. And so half of the participants said that this actually felt like rubbing. They actually used the term rubbing in their commentary. And so for the people who didn't, they said it felt kind of like a light grazing or light sweeping across their hand. Interestingly, one participant said it felt strangely comfortable, almost like the touch of someone else. It was more like a finger touching my skin than an object, which I think is interesting, if not a bit creepy. Okay, so it also turns out that taps and rubs are good for different things. Based on what people said they would use these types of things for, it turns out that they're good for things that vibration aren't. So on the one hand, people said that taps are good because they're quiet, and so they're not going to make a sound if this device is just kind of swinging around on the table at the library, whereas a vibrating phone kind of makes this sound and is still disruptive. Now, on the other hand, they said it's strong, which is good for loud environments where you might be on the move, and you wouldn't necessarily hear or feel your vibration, say, in your pocket. But because these taps bordered on the level of pain, they imagined that it was very likely that they would be able to feel these things if it was in their pocket. And I think it's worth pointing out that the rubbing is a little more subtle. So both from a perceptive standpoint and from kind of an applications standpoint. So from an applications standpoint, participants said that this would be useful in the hand scenarios where a vibrating phone is just uncomfortable. They mentioned that you probably wouldn't be able to feel a phone vibrating you in your pocket just because of it's kind of a very light sensation that I mentioned earlier. The other thing I wanted to touch on is just the fact that not all of our participants said it felt like rubbing, right? It had kind of this light grazing quality to it. And we think part of the reason for that is because we couldn't really control how much the actuator would push into the user's skin when it was rubbing across the surface. And you could imagine if we combined kind of the lateral motion of the rubbing device with the into the surface of the tapping, that you could basically regulate exactly how much you're pushing into the skin when you rub across. And that would essentially be combining tapping and rubbing into one device. Okay, so at a very high level, it turns out that yes, we can recreate tapping and rubbing to an extent using computer-mediated communication. And it turns out they're good for certain things that vibration isn't good for. But it also turns out that human touch isn't necessarily good for everything. So I alluded to this earlier, but psychology tells us that human touch is really good for emotive aspects, where you might be trying to get someone's attention, or you want to convey that you're really mad at them. But at the same time, it's not very good for semantics. You can imagine trying to organize a lunch meeting, for example, by using only human touch. I mean, I think that would be an incredibly hard problem, and I don't even know how you would do that. So it's not so great for expressing semantics. And so the question here is, well, can we bridge this gap, right? So we've kind of got this emotive aspect of touch going, but how can we convey semantics using touch? And that leads me to the final sub-project I'm going to talk about, which is actually something I'm currently wrapping up, which is a vibrotactile encoding of speech. And the idea here is that you could imagine this being used for two main applications. The first one that we started off with was looking at kind of this messaging back channel. You can imagine vibrating sequences coming from your phone telling you, someone is thinking about you, or some other lightweight communication message, I'm running a little late, something that doesn't necessarily need SMS to convey the information. A second, potentially more interesting application would be a form of augmented SMS. So right now, there's kind of this ambiguity associated with computer-mediated communication using text, because people are unable to express certain levels of kind of emotive aspects to their speech because these elements of prosody are actually missing from textual representation. And so you could imagine an augmented SMS message where you receive the visual text message along with an accompanying vibration that would potentially tell the user exactly kind of which words in the sentence are emphasized. And so as a pilot study to see whether this would even work, we took 5 common phrases from the text messaging literature, and we generated 4 different vibration sequences for each phrase. We recruited 20 participants, and in a forced choice response, we basically repeatedly presented these text phrases to users, and we played these different vibrations, and we said, hey, what does this vibration feel like? And we made them select one of these sequences, even though they might have felt a little unsure about it. And it turns out that participants actually do agree across the board on certain phrases mapping with certain vibrations. So shown here is the plot for the hello vibration. So I also have a demo of this on a phone, which you could feel after the talk. On the y-axis is amplitude, and on the x-axis is sample. And so you could see the pulse matching most closely to hello is kind of this medium level vibration, followed by a pause, and then kind of a really strong vibration. And shown here are the plots for are you busy, I miss you, goodbye, and where are you? So this was kind of a somewhat unstructured study just to get an idea of what elements of speech really are important for this kind of communication language. And so kind of moving forward, we decided, by looking at some of our results, it turns out that there seems to be some overlap between linguistic properties and kind of the different vibrations that we came up with. And so we're currently testing a number of hypotheses based on this. So first of all, it seems like the number of syllables is important, both based on looking at the confusion matrix, which I didn't show, and kind of the most successful phrases. It seems like different syllables should map to kind of demarcated vibration pulses. And looking at linguistic prosody, which is generally considered to be rhythm, stress, and intonation, it seems like these also map to different kind of duration and intensities of these vibrations. And an interesting insight here, kind of as a side note, is that linguistics tells us that prosody conveys a lot of emotive information in communication, which is kind of what got us thinking about this augmented SMS application that I talked about earlier. And so one insight is that rather than trying to map things like emotion and a bunch of other things that other HCI researchers are looking at, one possibility is that once we get the prosody down, if we just send this vibration sequence to someone else, they will kind of, based on that vibration sequence, be able to extract the prosody and presumably get a certain level of emotion out of that. And so I'm currently working on testing those hypotheses that I mentioned before in some user studies back in San Diego. Okay, so just to summarize today's talk, I opened up with an auditory feedback example. I presented a taxonomy that we use for kind of guiding our exploration in this space. And then I talked about a number of different projects that I worked on looking at how we might map music, human touch, and speech to the tactile channel. And really the high-level takeaway from today's talk, if you got nothing else, is that it turns out we really can take advantage of things that people are familiar with and map those to the tactile channel. And they come with some kind of information mapping for free, largely based on things that they're already familiar with. And so looking forward, you could imagine taking this idea, kind of everything that I've talked about today, which really, for the most part, even if you look at the greater haptics literature, really only focuses on how users receive information. It really focuses on kind of how we use tactile feedback, really, rather than tactile messages. But it says nothing about how users could actually convey this kind of information in a tactile messaging channel, for example. And you could imagine using the exact same approach that I talked about, where we try to leverage this pre-learned quality of human experience and using that for different tools for conveying information in these eyes-free scenarios. And so presumably this would lead to new tactile languages where people would be able to communicate, a whole new class of emotive communication where you'd be able to convey just lightweight emotional information. And finally, when you kind of combine this sending and receiving of tactile messages, I think looking forward, we're going to see this new class of devices that kind of supports this lightweight messaging channel that isn't really supported by SMS or email or phone calls currently. And so with that, I will take any questions you have. Mike.
Yeah, if you look forward and say, all of a sudden now some hardware manufacturer wants to make some version of what form factor would you see this embodied at? Obviously, wouldn't it be a big device? How would you make it a non or minimally invasive and augmenting a
phone? So given kind of what I've discovered so far, and without being able to predict what I'll discover in the future, I could imagine a kind of, first of all, taking out the current vibrotactile actuator in the phone and replacing it with two of the voice coil motors that I talked about in smaller form. So I imagine one being kind of attached to the side, which would generate this tapping sensation, and another one orthogonally mounted on the back that could kind of generate this rubbing sensation. The other thing I would mount is something similar to Ken Perlin's Unmouse, which is kind of, well, you know what it is, but for the people who don't know what it is, it's kind of this, it uses force-sensitive resistors. So basically it's a really thin, paper-thin-like sensor, which basically allows you to pick up both pressure as well as kind of location on the pad. So I have a.
That still requires you to get access to your device.
Right.
Whereas the vibrotac or the off-center weight means you can leave it in your pocket or close to your person and still get that one bit of information. So how would you? So
I think the actuators would be used for actually generating the actual taps and rubs. I bring up the pad because I imagine that to be an extremely useful sensor for picking up this generation of tapping and rubbing and other kinds of tactile messages. So before I knew about the Unmouse, I actually developed a prototype for kind of end-user generated taps and rubs, which hasn't been published yet. But the idea here is kind of a touchpad mounted on a pressure sensor. And so you tap it to generate taps. The harder you tap, the harder these taps are. And kind of the faster you rub, the faster these rubs get. And so you can imagine mounting this on the back of the phone. Obviously, this isn't nearly as cool as the Unmouse. And so if you had the Unmouse on the back, you could generate taps and rubs that way and send those to other people. Yes?
To get the rubbing, does something physically have to move, like a windshield wiper on the back of the phone, or can it somehow be inside the case and just transmit that feeling through the body?
So you could transmit it through the body. All the rubbing that we've done has been more of a skin-on-skin type of a feeling. So in some of our early prototypes, we actually played with doing the rubbing through a thin membrane. And you could imagine that's exactly what you would feel if the phone was actually in your pocket, right? Because it's not, I mean, unless you have a hole in your pocket, it's not going to be rubbing directly against your skin. So an alternative to the voice coil motor approach would be to use kind of two rotational motors. So it's kind of like tank treads, but you replace the treads with fabric, and then you can kind of generate some kind of rubbing sensation that way.
I was just wondering, could a jet of air achieve the same result.
I'm sorry. What?
Blowing.
Oh.
Because that might go through your clothes a little bit. I don't know. It might require too much power.
So, I know some people in Japan are working on a blowing kind of feedback device. So I think it's an interesting idea. My hunch is that. Yeah. So first of all, my hunch is that it would probably generate a different type of sensation. First of all, my second concern with that is really miniaturizability, because if you look at kind of their setups, they're all really big, and that kind of pneumatic setup would probably. I'm not sure how that would actually be miniaturized, but. Yeah, no, it's definitely interesting stuff. Yes.
I was interested how you talked about we use different auditory ringtones to represent different people calling, and that you could essentially do that with the vibrator as well. Based on the experiments you did turning the music into vibrations, how feasible is that to do kind of on the fly with existing technology?
So I guess everything that we did in that application could be done on the fly. The conversion wasn't that computationally intensive. It was done using MATLAB, but the tools, obviously exist. The main concern there is that right now it's somewhat semi-automatic. So you noticed I had those constants in there because it required a little bit of tweaking for different songs. And the other thing is, obviously we didn't map the entire song. We only selected a portion of the song that was particularly good for this kind of mapping. You could imagine some kind of automated mechanism for, like a two-stage classifier, first detecting which subset or which interval in the song would be good for this kind of mapping, and then trying to do it server-side. But currently it's not automated. But it could potentially be in the near future, maybe 2-3 years out.
Do you have any sense of how large a vocabulary in the last project that, for example, you asked people to map?
The speech one.
The speech
yes.
one, right. So, but how large the set of sentences that one can actually disambiguate it against?
So that's a good question. I actually think that the vocabulary there, so first of all, I don't know exactly how big of a vocabulary we could get in terms of trying to express text. But I actually think that by trying to express prosody instead of text, you first of all, you have a much more limited vocabulary of what you need to express, so that's good. But also you're able to express kind of new things that existing mechanisms can't currently convey. But off the top of my head, I would wager that users could fairly quickly be able to pick up somewhere between 10 and 20 different messages in a closed language that was used, over, say, an hour, I imagine. They could probably pick that up.
Convey direction, like doing sort of turn-by-turn guiding without having to look at a map later?
Yeah, so Hong Tan did this thing in the late 90s when she was a grad student, which was actually using sensory saltation. So that's basically where you have two actuators kind of physically located apart, where you play them off in quick succession, and that kind of gives you a directional feeling. And so you should actually use that as kind of a navigational guide. So if you imagine having kind of 4 actuators mounted on a device and firing off like the bottom one and then the top one in kind of with a phase offset, then you kind of get this directional feeling. And so, yes, I think that's a great idea. Someone should actually do it. But it has been studied.
Have you tried any of your experiments with people who have visual impairments?
I have not. So that's a good question. So some of the prosody work, I've actually been talking with some of the other folks at UCSD who are looking at kind of hearing impaired. And so we actually think that once we get the details of the algorithm down, we can use that to help users who used to be kind of who recently became hearing impaired to be able to learn sign language a little better than the current mechanisms, which seem to be really hard. So I think in that regard, there is some value, yes.
Have you looked at wearable technology, or maybe this being like an accessory to the phone? Something that you could be like more intimate and not like maybe when you're away from the phone, but it's kind of this more casual form of alerting the person.
Yeah, so I think that's a great idea. I think one of the nice things that you also touch on is kind of the fact that you can use different body locations instead of the thigh, which actually isn't so great for tactile feedback. So things like headsets or a watch, kind of in terms of accessories, I think would be really good for this kind of tactile messaging system. In terms of actual clothes, I don't know actually how you would kind of weave those actuators onto clothes in a way that kind of they can still go through the washer dryer. But
yeah, there's like this concept I saw a few years ago. It's like the hug shirt.
I saw that too.
I don't know how they do. I haven't, but
yeah. So that one was using pneumatics, I think. Mm-hmm. But it's a cool idea. I didn't actually get to try it out, but yeah, it's a good idea.
Let's thank Kevin one more time.